This is video number 14 in our topics of linear algebra. If you can go to the website at digital-university.org, there you will find the playlist for all the videos, because we're trying to make our presentation so there's a logical progression here. So if you hear us referring to previous videos that you haven't seen, they might be scattered all over the place on YouTube. But if you can go to the website, there you'll find all the videos there presented for you in their proper sequence. Okay, in this video we're going to discuss the null space. Suppose that we have two equations like this. We have x1 plus x2 plus x3 plus 0x4 equals 0. And 2x1 plus x2 plus 0x3 plus 1 times x4 equals 0. Or, as you've seen us do in the previous videos, the same two equations can be presented like this, where we take the columns, the coefficients, and make this matrix out of them, times a vector that has four components, x1, x2, x3, x4, and that equals the 0 vector that has two components to it. Now notice that this matrix has four columns, this matrix has four rows. And as you pointed out, I think it was in video number 9, on matrix multiplication, the number of columns in one matrix has to equal the number of zeros in the other matrix. And if we just multiply this out, indeed you'll see this is what we get, because we'll have x1 plus x2 plus x3 plus 0 times x4 equals 0. Same as this. And here we go across and down. 2 times x1 plus x2 plus 0x3 plus x4 equals 0. Same as this. Now, this matrix here is a 2 by 4 matrix. Two rows, 4 columns. This matrix here is a 4 by 1. Four rows, 1 column. And this is a 2 by 1 matrix. When you're multiplying matrices like this, eliminate the common number and you have a 2 by 1 matrix, and that's what you end up with. And we can write it in more general form like this: some matrix A times a vector, in this case the vector has 4 components to it, equals the 0 vector. And we want to solve for these components. So in other words, we're asking ourselves, A times what vector here gives us the 0 vector? That's what we want to solve for. So we just go ahead and set up our augmented matrix. Right here, 1, 2, 1, 1, 1, 0, 0, 1 equals 0, 0. There's the augmented matrix. And the first step is, we want, beneath this number, we always want to have number 1 here. We're all set to go with that. So we want to make this 0, so multiply by negative 2 and add to this row. I say multiply by negative 2 would just mean, in our imagination, these numbers stay the same. So negative 2 times 1 is negative 2. Add to that, that's 0. Negative 2 plus 1, that's negative 1. Negative 2 plus 0, that's negative 2. And these numbers stay the same because we're multiplying by 0. So we have it like this. Now here we can multiply across by negative 1, and we will have it like this: 0, 1, 2, negative 1, 0. And now, by multiplying this by negative 1 and adding, we can make this 0. So this stays the same, of course, and this is 0. And here's where we stop. You might think, well, wait a minute, we could add it again and make this 0, but if we do, then that won't be 0 anymore. So we stop at this point. Now, let's ask ourselves, in this matrix, what are the lead variables? So we're going along. Here in the second row, the first non-zero number corresponds to the x2 row. So x2 is a lead variable. And here, x1 is a lead variable. So x1 and x2 are lead variables. The leftover ones, x3 and x4, those are the free variables. And we first introduced this concept of free variables and lead variables, I think it was in video number 4. And we made a big deal out of it because we said we're going to use that concept over and over again throughout the videos. And indeed we have. Now what we do here is we express x1 and x2 in terms of the free videos. Let's look at this bottom row. Here we have x2 plus 2x3 minus x4 equals 0. And let's see, let's make some room here. We won't need this anymore. So from this, we say x2 will equal minus 2x3 plus x4. Okay, the lead variable is expressed in terms of the free variables. Now, let's look at the first row. Here we have x1 minus x3 plus x4 equals 0. So we have x1 will equal x3 minus x4. Okay, and this is really all we can say is that we can have an infinite number of solutions because the free variables are free. They can assume any value. So depending upon what values we choose for x3 and x4, that's going to determine what x1 and x2 are. So we can kind of write it like this. Let's get rid of this, I guess. x4 x3, x2 is this, and x1 is this. And there you see we've kind of expressed the whole thing as a giant column vector. But once we have it in this form, what we can do is we can factor out the free variables, the x3 and the x4. This would be equal to x3 times 1 times negative 2 times 1 times 0. Like this, plus x4 times negative 1, 1, 0, 1. Okay, x3 and x4 we said were the free variables. They can assume any value. So what that means is that This vector here, pretend this is just 1 and this is just 1. This vector here with components 1, -2, 1, 0, we put those numbers into here, you would get 0, 0. Or, if we put these numbers here, and put that into there like that, we would get 0, 0. Or, if we had any constant times this plus any constant times this, put it in there, you'll get 0, 0. So, first of all, the components of x that make this equation come true are called the null space. These two work in this equation. What's more, look at these vectors here. These two are linearly independent. Where this one has a 1, this has a 0. Where this has a 0, this has a 1. So there's no number that I can multiply this by to give us this vector. And same thing here, there's no number I can multiply this by to give this vector. So in the null space, we have two linearly independent vectors right here. Therefore, we say that the dimension of the null space is 2. But let's look closely how this happened. Originally what happened was we said, well, we've got lead variables x1 and x2, therefore we have x3 and x4 as the free variables, the ones that can assume any value. Therefore you're going to have an infinite number of solutions. So we said, well, what will this vector here look like? We said, well, the best we can write it is this. x4, which can assume any value, x3, which can assume any value, x2, we can write in terms of x3 and x4, so we have this, x1, which we can write in terms of x3 and x4, so we have this. What we can do is take one step further and factor out the x3 and x4. Add these together, we're going to get this. But now what makes it interesting, we factor out the x3 and the x4, we get two linearly independent vectors. Either one of these vectors put in here will make this 0. Any combination of these vectors will also make it 0. That's why we say there's an infinite number of solutions. This is a free variable. This is the free variable. So what this means is that for the null space, the dimension of the null space is equal to the number of free variables. Now, in the previous video, if we have just a general matrix, I'll just write a 3 by 3. Like this. And we look at these columns, columns, columns. What we said is that the dimension of the column space, the number of linearly independent vectors that are in the column space, is equal to the number of linearly independent vectors that are in the row space. And what determines that? The number of lead variables. So the number of lead variables determines the dimension of the column space, and it determines the dimension of the row space. The number of free variables determines the dimension of the null space of the matrix. And that's a concept that we're going to make use of in the next video when we start discussing eigenvalues and eigenvectors. But anyway, that's it for this video. Hope it was helpful to you. By all means, come back, join us for the next videos. We'll start working with eigenvalues and eigenvectors. Then that will set the stage. We can start to diagonalize matrices. So come back, Join us for those videos and we'll start solving some problems.